All right. So we've talked about the need for a rigorous definition of a limit that takes these issues into account. And I have this definition of a limit for you right now. So let's go through it and let's talk about what it means. So let's let f be a function defined on some open interval that contains the number a, except possibly at a itself. Basically, we need the function to be defined near a, otherwise it doesn't make sense to look at a limit. Then we say that the limit of f of x as x approaches a is L, and we write the limit as x approaches a of f of x equals L if, and this is the key, and this is also going to be something that most of you will find complicated when we look at it first, but this is how we close those loopholes. For every number epsilon greater than 0, there is a number delta greater than 0 such that if the absolute value of x minus a is between 0 and delta, that means that the absolute value of f of x minus L is less than epsilon. Now, I'm sure that means nothing to you right now, but remember that the absolute value actually refers to distance, right? The absolute value of a number is defined as the distance between that number and 0 on a number line. And when we have the absolute value of a difference of two quantities, that actually means the distance between those two quantities. So what this means is for any positive number epsilon, if we're given a number epsilon, we're able to find a number delta such that if the distance between x minus a is less than delta, we need it to be greater than 0 because we don't want x to be equal to a. Remember, one of the golden rules with limits is we don't care the value at a, only nearby. So this says if our x value is less than delta units away from a, that means that the function value is going to be less than epsilon units away from L, from this supposed limit. What this means is that we can make our function values as close to L as we want for any value of epsilon by making sure that we're picking x values close enough to a, and we have to find kind of a domain that we're looking at, or a small enough neighborhood to make sure that our x values give us function values that are close enough to L. Now, I want to look at those two example graphs that we had where it looked like maybe the limit existed, but it didn't, and show you how those two kind of break this definition, how they break these rules. So for this first one here, remember there was this problem that we had a gap. Now remember, this precise definition of the limit says that we can make our function values as close to the limit as we need to by picking x values that are close enough to a. But here's the thing. If we pick epsilon equal to 0.01, then we need x values such that our function values are less than this distance away from the limit. But here's the thing, there is no part of this graph where the function values are less than 0.01 away from 0. Right? Remember, we thought maybe the limit was 0. What we would need is we would need some sort of part of the domain where the function values stayed in between this area from negative 0.01 to positive 0.01. We would need an area where the function is staying in between these two y values, But in this case, it never goes in between those two y values. There's a gap. We need to make sure there's no gap for that limit to exist. And unfortunately, this one has a gap. But there's a second thing that can go wrong, and that's illustrated in the other graph. And so if we look at this function, remember this one also, when we had zoomed out, it looked like maybe the limit as x approached 0 of this function was 0. Now, this precise definition says that for any epsilon greater than 0, we are staying within that range within that distance of what we thought the limit was. Now, if we pick a large value for epsilon, for example, if we're picking epsilon to be 0.03, we need to stay in between positive 0.03 and negative 0.03. There needs to be an open interval on the x-axis where the graph stays in between these two y values. And we have that, which is really lovely, right? You can see here, even though on the outside the graph is going to be too big, if we look in between 0.1 and negative 0.1, give or take, we are staying within the range that we need, within this epsilon, within 0.03 in either direction. But the problem is that if we pick a smaller epsilon, say 0.001 or 0.05, basically if we take a smaller value of epsilon, there gets to be a point where the width of, or the height, I guess, if you want to call it, of this distance is less than how much our graph is oscillating. Our graph is oscillating too much here. It never stays within this smaller range. It stays within this larger range, with a larger value of epsilon. It's going to stay in between. But there gets to be a point where if we make the epsilon too small, our y values never stay within it because they continually oscillate too high and too low. So this bit right here of this definition says there isn't a small enough neighborhood that we can look at where our function is always bounded above and below by 0.01 or 0.001 and negative 0.001. I can't actually see what this distance is, but there gets to be a point where, unfortunately, our function is oscillating too much, and it doesn't matter how much we zoom in, how small of a neighborhood we're looking at for our x value, the y values keep getting too large and too small. So basically, there can't be a vertical gap that our function doesn't go in between. And then for any vertical distance, there needs to be a neighborhood around the value that we're looking at where our y values stay within that vertical range. And it doesn't matter what the height of that range is. For any epsilon greater than 0, so for any height, we need to be able to find a neighborhood that our function stays within that vertical range.